Pluto's orbit has always posed potential complications. Its path crosses that of another planet, which has raised concerns since the very beginning. Pluto, a small and enigmatic planet located at the furthest reaches of our solar system, has become a topic of significant interest in recent astronomical discussions. Recent reports indicate a possible collision with Neptune, which has raised alarms within the scientific community and among space enthusiasts. Well-known scientists such as Neil deGrasse Tyson and Michio Kaku have voiced their apprehensions about the possible repercussions of such an event. But what led Pluto to be on a collision course with Neptune, and what could this cosmic confrontation mean for Earth? Join us as we delve into the details of this potential galactic clash and explore why astronomers are concerned about this unusual cosmic behavior. Once considered a full-fledged planet, Pluto was later reclassified as a dwarf planet primarily because of the eccentricities in its orbit. Despite this downgrade, Pluto continues to intrigue and capture the imagination of astronomers and space enthusiasts alike. Recent statements from experts like Neil deGrasse Tyson and Michio Kaku have suggested that Pluto's orbit might cross Neptune's path, raising the possibility of a dangerous collision with severe consequences for our planet. Pluto's journey around the Sun is truly remarkable due to its unusual characteristics. Its orbit is extremely long, taking a staggering 248 years to complete one full revolution. Since its discovery in 1930, Pluto has not yet completed an entire orbit around the Sun. What makes Pluto even more intriguing is the highly elliptical shape of its orbit, which contrasts sharply with the nearly circular orbits of the major planets. Additionally, Pluto's orbit is tilted at a 17 degrees angle relative to the ecliptic plane, resulting in a much steeper path compared to the orbits of the other planets. This combination of orbital tilt and elongated shape complicates Pluto's motion, making its path unique. A fascinating feature of Pluto's orbit is that it repeatedly intersects Neptune's orbit every 20 years. At these points, Pluto's path takes it closer to the Sun than Neptune, which defies our expectations of how the planets should be positioned in the solar system. Further analysis reveals that Pluto's orbit is far from a perfect circle. Instead, it follows an elliptical or oval trajectory, causing its distance from the Sun to fluctuate considerably. At its closest, Pluto comes within approximately 30 astronomical units, AU, of the Sun, but at its furthest, it stretches to more than 49 Australian dollars, nearly double Neptune's average distance from the Sun. Moreover, Pluto's orbit is inclined at an angle relative to the other planets, further complicating its interactions with Neptune. This inclination is key in understanding how Pluto and Neptune interact when their orbits cross. The gravitational forces between the two bodies pull at each other, gradually altering their respective trajectories. This dynamic relationship underscores the interconnected nature of the solar system, where the gravitational pull from one planet can influence the movement of another. Thanks to advancements in technology and improved observational instruments, astronomers have been able to track Pluto's motion with increasing precision. This has allowed for a clearer understanding of its orbit and the potential effects it may have on the overall stability of the outer solar system. While the likelihood of a direct collision between Pluto and Neptune is low, the possibility is being actively studied, as the consequences of such a collision could be catastrophic. Despite Pluto's small size and its remote location, it continues to captivate scientists and space fans alike. A central question remains: why hasn't Pluto collided with Neptune already? The answer lies in the gravitational influence of other planets. Since Pluto's discovery, astronomers have been working to understand its peculiar orbit. Unlike most planets, which follow relatively consistent paths along the ecliptic plane, Pluto's orbit is distinct due to its steep angle and elliptical shape. The mystery deepened when it became clear that Pluto's orbit crosses Neptune's. Despite this apparent danger, Pluto's orbit has remained remarkably stable, demonstrating the complex forces at play within the solar system. The study of how Pluto, Neptune, and the Sun interact presents a significant challenge for astronomers. Predicting their movements requires a deep understanding of the gravitational forces that influence one another's paths. To help solve this cosmic puzzle, scientists rely on several specialized terms, including ASMU libration, latitude libration, VSOP, and Steves and Kaplan isolation. For instance, ASMU libration plays a crucial role in maintaining the stability of planetary orbits. When Pluto crosses Neptune's orbit, it remains at least 90 degrees away from Neptune, ensuring that a direct collision does not occur. Latitude libration helps ensure that Pluto remains positioned above Neptune's path when it approaches, reducing the likelihood of a collision. The VSOP oscillation, named after scientists von Zeipel, Steves, and Kaplan, explains why Pluto's orbit appears odd yet remains stable over long periods. Even though space seems chaotic, there are underlying patterns that prevent Pluto from colliding with Neptune or significantly altering its trajectory. The concept of orbital chaos describes how a celestial body's path is highly sensitive to its initial position. Even minor changes in Pluto's starting position or velocity can have profound effects over long periods. To model Pluto's interactions with Neptune and other bodies in space, scientists use advanced computer simulations. These simulations explore the potential consequences of even the smallest changes in Pluto's trajectory. In the late 1980s, these simulations uncovered a fascinating result. Despite Pluto's seemingly stable orbit, it can still behave unpredictably. A slight shift in Pluto's position or speed could lead to significant changes in its orbit over time. However, even with these uncertainties, Pluto's orbit has remained stable for billions of years, suggesting that despite its erratic motion, it follows an underlying order. The unpredictability of planetary orbits, such as Pluto's, makes it difficult to forecast long-term changes with certainty. These models require highly precise initial conditions, as even small errors in the data can lead to vastly different outcomes, making accurate predictions extremely difficult. Understanding Pluto's orbit is especially important when considering the possibility of a future collision with Neptune. This knowledge contributes to a broader understanding of how our solar system functions. Pluto's orbit serves as an example of how paths that seem chaotic can eventually reach a balance, guided by gravitational forces and motion. It is essential that we continue to monitor and study these celestial dynamics to gain a clearer understanding of our place in the universe. Pluto's orbit offers a textbook example of the unpredictable nature of space. Unlike the orbits of the other planets, Pluto's path is highly elliptical, leading to unpredictable encounters with Neptune. This irregular motion makes it challenging to predict the long-term behavior of the system. However, gravitational forces play a crucial role in preventing Pluto and Neptune from colliding. Gravity, the force that pulls objects toward one another, ensures that, despite their overlapping orbits, the two bodies remain apart most of the time. These gravitational interactions demonstrate the delicate balance of forces that govern space. While a direct collision between Pluto and Neptune remains unlikely, such an event would have enormous implications for our understanding of the solar system. The release of energy from such an event would be immense, and the debris scattered across space could have far-reaching effects, potentially impacting other planets and moons. Neptune's orbit itself could be altered, further complicating the dynamics of the outer solar system. As space exploration continues to advance, Pluto's orbit serves as a reminder of the many uncertainties that still exist. Scientists continue to study Pluto's trajectory to better understand how large planets influence its motion. This knowledge is essential for understanding the intricate relationships between celestial bodies and how their movements might affect one another. Despite the unusual nature of Pluto's orbit, some of the world's foremost scientists, like Neil deGrasse Tyson, have speculated that Pluto could eventually collide with Neptune. Tyson, a renowned astrophysicist, sees Pluto's reclassification as a dwarf planet as an important step and emphasizes the need for continued exploration. He believes that Pluto's eccentric orbit underscores the fact that much remains to be discovered about space and the forces that govern it. According to Tyson, it is the mysteries of space that make studying it so compelling, and he encourages others to explore the fascinating complexities of celestial mechanics. Tyson, along with other experts, expresses concern over the potential dangers posed by Pluto's unusual path. If a collision were to occur, it could have catastrophic consequences for the solar system. The release of energy from such a collision would be immense, and the debris scattered throughout space could affect other planets and moons, potentially altering their orbits. Theoretical physicist Michio Kaku, known for his work in string theory, also offers valuable insights into space exploration. Kaku believes that studying phenomena like Pluto's orbit is crucial for understanding the broader principles of celestial mechanics and theoretical physics. He suggests that studying Pluto's interactions with Neptune could help guide future space missions and improve safety in space exploration. Kaku also underscores the importance of understanding gravitational forces in the context of space exploration, as these forces could shape the future of how we explore distant planets. Kaku's work in string theory, which seeks to explain the fundamental forces of the universe, aligns with his interest in Pluto's orbit. A collision between Pluto and Neptune could provide valuable data that would contribute to our understanding of gravity and spacetime, central concepts in string theory. While a collision between Pluto and Neptune would likely have minimal direct impact on Earth, it could offer a unique opportunity to study the behavior of fundamental forces under extreme conditions. As scientists continue to explore the far reaches of space, the unpredictable nature of planetary interactions becomes more evident. Studying celestial dynamics, such as the gravitational relationship between Pluto and Neptune, provides valuable insights into the fundamental laws of the universe. By continuing to observe and study these phenomena, we are moving closer to understanding the vast and complex nature of the cosmos. The gravitational interaction between Pluto and Neptune highlights how even distant planets can influence one another. These celestial bodies exert gravitational forces that can subtly shape their orbits over long periods. While the likelihood of a direct collision remains low, the possibility is not entirely ruled out, keeping scientists interested in monitoring the situation. They believe that by understanding these forces, they may one day be able to predict and mitigate the risks associated with such cosmic events. An intriguing aspect of planetary motion is how seemingly random interactions can lead to stable and predictable patterns. This is evident in Pluto's orbit, which may appear erratic but is, in reality, governed by precise gravitational forces. These forces help prevent Pluto from colliding with Neptune, despite the apparent overlap in their paths. The delicate balance between the gravitational pull of other planets and Pluto's orbit ensures that the dwarf planet follows a steady, though complex, course. Understanding this intricate relationship is key to advancing our knowledge of the broader solar system. As scientists continue to explore Pluto's orbit, they also look toward other areas of space exploration. For instance, studying systems like the TRAPPIST-1 system, which contains multiple Earth-sized planets, helps astronomers understand how gravitational forces between planets can lead to orbital resonances. In some cases, this can increase the chances of a planet's orbit becoming unstable. Though the TRAPPIST-1 system is not currently facing any collisions, scientists remain vigilant, tracking the movement of planets in these crowded environments to better understand the risks and how they might evolve over time. Meanwhile, astronomers are also focused on understanding the behavior of rogue planets, which wander through space without being bound to any star. Rogue planets, which travel through space unattached to any star, present an entirely new set of challenges for astronomers. These planets, not bound by the gravitational pull of a star, drift freely across the galaxy, making their orbits unpredictable and difficult to track. Unlike the planets in our solar system, which are influenced by the sun's gravity and follow more or less stable orbits, rogue planets can be subject to the gravitational influence of passing stars or other celestial bodies, which can significantly alter their paths. While rogue planets are a relatively new area of study, their behavior offers valuable insights into the dynamics of planetary motion and gravitational interactions on a much larger scale. The discovery and study of rogue planets could help astronomers refine their understanding of planetary formation and the forces that shape the orbits of planets within solar systems. These free-floating planets do not conform to the usual rules of solar system dynamics, so studying them could reveal new aspects of how planets interact with one another, as well as how planets can form and evolve without the presence of a host star. This information might also offer clues about the potential for life on planets that do not orbit stars, a question that has intrigued scientists for years. Moreover, rogue planets may provide a unique opportunity to study the effects of gravitational interactions in isolated environments. With no star to anchor them, these planets rely on the gravitational forces of nearby objects to influence their movement. This makes them an intriguing subject for exploring the potential effects of gravitational forces in more chaotic, less predictable conditions than we see within our solar system. Understanding rogue planets could also contribute to the broader field of space exploration. If we are to explore other star systems and potentially colonize planets, the study of rogue planets and their trajectories may play a key role in predicting their behavior and identifying any potential hazards. Additionally, examining rogue planets could help us learn how to design spacecraft that can navigate complex gravitational environments, including those that involve wandering planetary bodies. The study of Pluto's interactions with Neptune also brings to light broader questions about the future of our solar system. As our understanding of planetary orbits continues to deepen, we must consider how the positions and movements of the planets could shift over time. While a collision between Pluto and Neptune is unlikely, the possibility of such an event underscores the fragile nature of our solar system's structure. It reminds us that the gravitational forces between planets are not static. They evolve over time, sometimes leading to unexpected results. Over millions and billions of years, even minor changes in the position of a planet can have profound effects on the system as a whole. For example, while Pluto's orbit appears stable today, it is possible that small gravitational interactions with other planets or celestial bodies could alter its path in the future, bringing it closer to Neptune or leading it on a more erratic course. This is why scientists continue to monitor Pluto and other distant objects in the solar system, looking for signs that their orbits are changing and predicting how these changes might affect the overall dynamics of the solar system. In fact, the study of such long-term orbital changes is crucial for our understanding of the future of the solar system. The movements of the planets and other objects are governed by complex gravitational interactions that can evolve over time, potentially leading to new alignments or even the ejection of objects from the solar system. Understanding how these forces work allows scientists to predict and model how the solar system might look millions or even billions of years from now. For example, some scientists theorize that, over an extended period of time, the gravitational influence of the planets could cause their orbits to shift, eventually leading to the destabilization of the current configuration of the solar system. Such a shift could result in the eventual ejection of one or more planets or even the collision of two planets, although this is an event that would occur on a timescale far beyond human lifetimes. In addition to planetary interactions, the study of other celestial bodies, such as asteroids, comets, and moons, also plays a crucial role in understanding the future dynamics of the solar system. Many of these objects have irregular orbits that can bring them into closer proximity to the planets, raising the potential for impacts that could have significant consequences for the solar system. By studying the orbits of these smaller bodies, scientists can better predict the likelihood of collisions and take steps to mitigate potential risks.